It is a project, area estimation of a region. Every bounded region in the two-dimensional space can be saved via a simple closed curve. In the case, we can compute the area of the region effectively using a line integral along the curve. That would be an application of Green's theorem. Look at the figure. It is a brain tumor example in an MRI scan. I got it from this paper. In the image, tumor cells are detected, and by using a segmentation algorithm, we can get this region, and it can be saved using just the boundary information can be saved so that it can be a curve. Then along the closed curve, we can estimate the area quite effectively. Let's see the Green's theorem. C is a positively oriented, piecewise smooth, simple closed curve in the plane, and D is the region bounded by the curve. F, PQ has continuous partial derivatives on an open region including D. Then the line integral along the curve C, P dx plus Q dy, can be obtained through this regional integral Q x derivative minus P y derivative. We'll apply this formula with a special choice. P is 0, Q is x. Then Q x derivative, that is 1. P y derivative, okay, that's 0. So this quantity is 1. So in this position, there will be 1, which is this one. But this one is the area of the region. Now, with the choice, P is 0, Q is x, this line integral becomes this simple form. So for the area of the region, we can get the area through the line integral and x dy. Okay. Here are project objectives. Derive a numerical method for the line integral. Then it will be the area of the region. Implement a code for the computation of areas. Okay. In reality, the region of interest is saved by a sequence of points. For example, a region is given in this way. Now we'll try to approximate the region using a finite number of line segments, and that can be represented by these points. x0, y0, the beginning point, x1, y1, x2, y2, and turn around, and the last point is xn, yn. So the last point is the same as the first point. That would make a closed curve, an approximation. Now we'll try to find the area of this approximation. That is not the same as the original area. However, if you try to choose more points and more, then the area will be more accurate. So that assuming the number of points are big enough, and we can say that this estimation is quite accurate. Here we have a question. If a sequence of points represents a region, how can we compute its area accurately? Let's try to derive a computational formula. The first example is along with a rectangle. For rectangle AB and CD, the area can be easily obtained. This is length times height. But this one can be rewritten in this way. Okay, the same as this one, and we can recheck that one. Now this one, this portion is for that side, and side by side we consider the quantity. Now that is, the x value is b, change in y is positively oriented, so they're coming up. So change in y is d minus c. That's exactly this one. And for that side, now x value is a, and change in y is from d to c, so that's c minus d. Now, this horizontal sides, and there's no change in y, and also no change in y. So along with change in y, we have contribution. So we may guess the formula, the area must be x value times change in y. Now rather than x value, we try to use the mid value. Of course, along that the line segment, the mid value of x is the same as b, because in x direction no change. But once it is changing in x direction, then we'll try to mid value of x. Let's apply this formula for this computation of area of a triangle. Okay, for this triangle, the area is easy to get. Half times b minus a, that's bottom length, and d minus c is a height. Quite easily we can get the area. Now we'll try to apply the formula. Okay, that is, for the first one, mid value of a, EV value of x is a and b, so that half of a plus b, and y value, there's no change, c to c. Okay, we have that. Now for second line segment, the mid value of x is b and b, so that one, and y value is changed from c to d, so d minus c. For the last one, now the mid value of x is b plus a, ab over 2, and y is changing from d to c, the second component, that is d and c, so the c minus d. If we simplify these quantities, then we can reach at the same result. So at least for this example, the formula is correct. Okay, let's try to one more. Now, for this figure, shaded area and maroon colored, and the area is 30 because total area is 36. The area of this portion is 2, that is 4, so that 6 will be subtracted, so we can get 30. So let's try to check if the formula is correct. We'll consider only non-zero contributions. For that one, there's no change in y, so no contribution. For this one, x value is 2, and y is changing from 0 to 3, so change in y is 3. So along this line segment, the contribution is 2 times 3. Okay, that is exactly that one. Now, for that one, the mid value of x is 2.5 and change in y is -2. That is this one. Now, for that one, now mid value of x is 3.5, change in y is 2. So that is this one. And now for this one, and x value, mid value of x is 4, change in y is -3. That's that one. Now, no contribution for this one. X value is 6 and change in y is 6. So that 6 times 6. Now, no contribution for that one. Mid value of x is 3.5 and change in y is -2. That one. And for this one, now mid value of x is 2.5, change in y is 2 from here to there in y direction, and the change is 2. Now for that side, no change in y, so it's 0. For that one, now x value is 0, so that here, even though change in y is -6, is going down, so from 6 to 0, so it's a -6 in change in y, but x value is 0, so that again, no contribution. So we have all here the contributions, non-zero contributions. We simplify, and then we can get 30. Okay, the formula is correct for also this example. We summarize our derivation here. Region D is represented as a sequence of points x0, y0 to xn, yn for a positive integer. Of course, the terminal point must be the same as the initial point. Now, Li is the ith line segment connecting from this point to that one. Then the area of the region can be computed using the formula. For each line segment, we try to get mid value of x and change in y, and the product will be summed. And that is the area of the region. That's the formula. But for this formula, it is not yet, we don't know yet, it is correct for all cases. So we need a little bit of accuracy analysis. The numerical formula in this equation is exact when the closed curve C consists of line segments only. Let's look at the proof. We focus on the first line segment and the C1 connecting from now P0 to P1. Then the numerical formula is giving this one in the along the first line segment, mid value of x times change in y. Okay. Now for the line segment, we'll try to get exact value. In order to do that, we need a parameterization R1 over T I'm sorry, I got cold, and as you can hear, my voice is already gone. I'm sorry about that. R sub 1 of T, the parameterization can be made in this way. 1 minus T initial point plus T the terminal point. We can rewrite in this way, and component wisely we can write in this way. Of course, T is between 0 and 1. then the line integral over c1 x dy can be written here, integral from 0 to 1, x of t, y prime t, dt. That is x of t, that one. And this is y. And y prime is y1 minus y0. That is y prime. And dt. y1 minus y0 is a constant. We can put this one outside the integral. And for the remainder part, we try to find the antiderivative of this one. And so that is x0t plus, okay, that one will become t squared over 2 x1 minus x0. And we are evaluating this antiderivative between 0 and 1. Then we can simplify to get the result. This is the same as that result from the formula, which means that the formula is exact along the first line segment. But this argument can be applied for every line segment, so that this formula is exact when the closed curve includes only line segments. Okay? Okay, we have one example. We'll try to generate a data set and plot it and measure its area. For example, for this ellipse, we can generate a data set. Xi, yi can be 2 cosine theta I and sine theta I. So that is x component, y component. So from this one, now x over 2 equal cosine theta I. And from the second one, now y is sine theta I. The square, summation is 1. That's exactly this one. So it is parameterization of the ellipse. Okay. Well, of course, we can easily see that the last points must be same as the initial point when theta I is obtained through this formula. I times, that is basically delta theta, 2 pi over n. We can analyze accuracy improvement of the area as n grows. And if we try to choose larger n, then we can get a better accuracy. The area made by this ellipse is now 2 pi, right? And it's known that this is a major axis, A, so that for general ellipse, x squared over a squared plus y squared over b squared equal 1. For this one, the area is AB pi. Right? So the area of this ellipse is 2 pi. Let's see this program. A is 2, B is 1. So the true area is AB pi. Now we have 4 different choices of n saved in partition 10, 20, 40, and 80. For each n inside this array, so n will become 10, 20, 40, 80 in this loop. The first one is 10. Now we try to make a theta that is between 0 and 2 pi and n plus 1. Beginning in MathLab is x1, so the theta 1 will be 0, and theta n plus 1 will be 2 pi. This is whole circulation of the theta. And then we try to get the data. This is x component and y component. That is exactly now that data set. By using the data set, we can get area close the curve. You have to implement a program for this operation. I did this myself, but I'll not reveal this one. That is a major part of the project. You have to make this one yourself. Now, after getting area, we try to print out the estimated area, and at the moment the error. So the area and true area, the difference will be divided by the true area, so that this quantity is the relative error. Okay. Now you can plot the approximated region, and also you can save. Okay, that's the program. So it is not really necessary, but if you want to see the plot, then you can put this portion. Now from this one, we can get output. And it's moving from 10, 20, 40, and 80. The estimated area is given in this way. At the moment, the relative error, so in the beginning, it's about 6%, and it becomes about 1.6%, and 0.4%, and 0.1%. From this output, you can see that once you try to choose twice more points, then the error becomes quarter. So the convergence is quadratic. So it's in a sense, the angle becomes half for each line segment. Now the error becomes quarter. So half squared is quarter. So it is quadratic convergence. Okay. Now these are figures for approximate ellipse. When n is 10, we have this line segment quite vividly. When n is 40, then it's not easy to see the line segment, but each one will be a line segment and 40 subregion. Okay, that is approximate ellipse. For this one, the area, relative error, is about 0.4%. Okay. Here are what you will do. Number one, data is given. So by clicking or by writing this one on web, you can download. And after downloading this data set, you can draw a figure and use the formula to find the area. So basically, you can import, rather than this generation, you can import the data set, and then by implementing this function, you can get area. That's the first one. And number two, repeat part one for another data set. For the data set, extra data set, you can search the internet, or you can generate a data set. For example, a cardioid, the parameterization of a cardioid can be given in this way, so that if you choose this option, then over there you may replace this portion correspondingly for that parameterization. Then the data will be made. In this case, the area of the cardioid will be 6 pi a squared. So you may choose 1a, for example 1 or 2. You can choose a value for a. Here is some warning or what we have to do. The last point must be the same as the first one. And the larger n you choose, the more accurately the data would represent the region, as we did for this ellipse. Analyze accuracy improvement of the area as n grows. Your report should include your code, outputs, and concluding remark. I hope you enjoy the project. Thank you.